It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappinin'? Today, we're going to talk about how your weight changes in an elevator. Have you ever ridden in an elevator, and when it accelerates upwards, the moment it starts moving, you feel that uneasiness feeling where you appear to be a little bit heavier? Or if it accelerates downwards, you feel like that weightless feeling, or if you were to jump in the air, you could jump higher. The same idea goes for roller coasters. If you're going up, you kind of feel heavier. When you're accelerating downwards, you feel like your weightlessness a little bit. So what we're going to do is imagine I'm standing in an elevator right now, and I'm on this blue scale, and that's what my mass reads. Now, let's label the forces acting on me while I'm standing on the scale. Right now, going downwards, we have the force of gravity. When I stand on the scale, I'm pushing down on it due to my force of gravity, and the scale is pushing upwards on me. That's the number that the scale reads. We're going to call that the normal force. So going upwards, I'm just going to draw it longer so you can see it. The upward force, or the reading on the scale, is the normal force. So let's look at what happens when you just walk in the elevator and it's not moving. So let's look at a stationary elevator. Let's leave a little bit space in between here because we're going to add something afterwards. And to look at how our weight appears, let's start with Newton's second law, which is A equals the net force all over the mass. We want to break down the net force into the two forces that are acting on me. F of n is going upwards, the normal force, minus F of g is going downwards, all over the mass. We can multiply both sides by the mass. So m times a is equal to Fn minus F of g. When the elevator is not moving, its acceleration is 0. If we add Fg to the other side, my weight is equal to what the normal force is, or what the reading of the scale says. So when you're not moving, Fg is equal to Fn, the normal force. We said that you're not accelerating when you're not moving, but you can also be moving at a constant velocity to not accelerate. Which means after the elevator starts moving up or down, that in-between process while it's moving at a constant velocity. So after the elevator initially accelerates, it starts moving at a constant velocity, which means Fg is equal to Fn when you're in a stationary elevator or moving at a constant velocity. Let's look at the instance in which the elevator is accelerating upwards. We're going to start with Newton's second law, A equals F naught over m. break it down to A equals Fn minus Fg over M. And then we could do, let's do this like this, sorry. A equals F sub n minus F sub g all over the mass. We'll multiply both sides by the mass, so Ma is equal to F sub n minus F sub g. We want to figure out what happens to the reading of the scale, or what you feel like, and again, that's the normal force. Let's add Fg to the other side. F sub n equals your mass times the acceleration of the elevator plus F sub g. F sub g is your weight, or the force pulling down on Earth, the force due to gravity. We could simplify this even further if we want, and break down F sub g into mg. Which means the weight on the scale reading, the normal force on the scale reading, or your apparent weight, is the mass times acceleration plus your mass times the acceleration due to gravity. Which means when an elevator is accelerating upwards, your Fn increases. Sorry for the screen moving. Fn increases, which means your apparent weight increases. You're going to feel heavier while the elevator is accelerating upwards. One more time. Let's now do it when the elevator is accelerating downwards. We could go back to where we started with mass times acceleration equals Fn minus F sub g. We want to solve for the normal force, so we'll add Fg to the other side. That gives us F sub n is equal to Ma plus F sub g. However, in this case, we said that the elevator is accelerating downwards, which means this A is negative. So why don't we just put it on the outside for now? That gives us Fn is equal to F sub g minus m times A, the acceleration of the elevator going downwards. And we could see that because we're subtracting this to your normal weight or force due to gravity on Earth, the scale is going to read a smaller number compared to when you were stationary. Which means your apparent weight, F sub n, decreases and your apparent weight decreases. So just to reiterate, when an elevator is stationary or moving at a constant velocity, your weight, the force due to gravity, is equal to Fn, what the scale reads. When it's accelerating upwards, your weight is going to be heavier, so it's the mass times your mass times the acceleration of the elevator plus your mass times the acceleration due to gravity. If you were standing on a scale, you would see that this number on the scale would increase, which is your apparent weight increasing. When you accelerate downwards, the opposite happens. Your apparent weight will decrease because the elevator is accelerating downwards, subtracting from the force due to gravity. What do you think would happen if somebody cut the cord on the elevator and now you're in free fall motion? We'll talk about that in class. Right now, however, I'm going to tag 2 links on YouTube of me riding in an elevator and watching what happens to my apparent weight as it accelerates upwards and downwards. That's it for today. Thank you for watching, and I'll see you next time. See ya!